Good afternoon, everyone, and welcome to today's webinar on SoMat eDAQ Common Field Problems and Solutions. Your microphone will stay muted throughout the presentation. If you have questions, we will address them at the completion of the presentation using the Q&A feature of WebEx. However, you're welcome to type in the questions at any time. Our presenter today is John Bodorf. John is currently the HBM Technical Support Manager, responsible for technical support for all HBM products in North America. He's been with HBM for over 7 years, working in repair, sales, and technical support. He currently works out of our Champaign, Illinois office. John, it's all yours.
Hello, this is John Bodorf from HBM Technical Support. Today we will be talking about SoMat eDAQ Common Field Problems and Solutions. We will be discussing some of the most common problems reported from the field. I will not be able to discuss in great detail all of the possible problems seen by you, our customer, but I will endeavor to touch upon issues that I feel will be most beneficial to you. The intent of this webinar is to give you the tools to identify and correct, if possible, common problems often seen with SoMat eDAQ data acquisition tests. This webinar was authored assuming that attendees have a working knowledge of the eDAQ and its associated hardware and software. Also, just a quick note that the version of TCE you're using may not exactly match what I have used here today, but for the most part they are all very similar in functionality. In today's webinar, I will make a few references to the eDAQ manual. This is the manual that is available in TCE under the Help tab. It is fully searchable, and while I have referenced specific sections, you could easily find these sections using the search function of the manual. Today we will touch on the subjects noted here. Chapter 1 will be System Basics, or just a few important parts of the eDAQ that we need to take a look at. Chapter 2 will be Troubleshooting aids available to us. Chapter 3 will be a few of the most common problems reported from the field. Chapter 4 will be troubleshooting using front panel indicators, or as you guys probably already know, the front 3 LEDs. Chapter 5 will be troubleshooting using TCE or Logfile. And then Chapter 6 will look at a couple of special cases as in networking and vehicle bus hardware. For this discussion, we will focus mainly on the eDAQ Plus, as the functionality of the eDAQ Lite is the exact same as the eDAQ Plus. Differences between eDAQ Plus and Lite is the Plus can have an embedded communications layer in the base processor, either an ECOM or an HLB-VB layer. Lite communication layer is always separate. The Plus has external compact flash capability, while the Lite does not. Once we have discussed the physical placement of components, we will only refer to the Plus. We will not discuss the eDAQ Classic in this presentation. It is approaching end of life, and I would encourage any of you having resources to replace your Classics with Pluses if at all possible. While we still support and repair it, it cannot utilize the latest firmware capabilities. As an example, TCE 3.9 does not support our current video streaming capability. For reference purposes, the eDAQ Classic can only be used with TCE 3.9 and below. This version was frozen 6 years ago, and currently we are up to TCE 3.18. So here's the physical components, or location of some critical components in eDAQ Plus. Obviously, we pulled up the bottom plate, and this is the bottom view of the actual Plus processor. First, there's the battery. Okay, there's no clock calendar battery in the eDAQ Plus, only the battery that is located on the bottom plate of the unit. This battery is for graceful shutdown purposes. There is sometimes confusion as to whether or not the eDAQ can run when power is disconnected. This battery can help power the eDAQ during cold cranking operations, but once power is lost, the battery supplies the necessary power needed for the eDAQ to shut down without losing data or corrupting its firmware. The eDAQ does not need to be on to charge the battery. It only needs to be plugged into a good power source. Our next item is the fuses. Okay, there are two 10-amp automotive bayonet fuses on the bottom of the eDAQ. These same exact fuses also appear in the eDAQ Lite. Of note is that the inside fuse is the negative or the low side fuse, and the outside fuse is the positive. Okay, our next item of interest is the internal compact flash. The compact flash shown here holds the boot up program for our system. Additionally, the internal compact flash is our main data storage device. There's oftentimes confusion in the field as to what and where our main memory is. The external slot is only capable of data storage. It holds no information for system boot up or operation. You do not need a flash card in the external slot for system operation. We recommend that you only use the external slot for storage when you have to hot swap memory cards in the field. If you're able to access the machine with a computer, downloading data from the internal card is very simple. Additionally, the internal slot is capable of higher data throughput speeds than the external slot. Here's a bottom view of the eDAQ light. Okay, the light battery, like the plus, is on the bottom plate. I did not show it here as I wanted to point out the battery cable plug. Later in this webinar, when we talk about disconnecting the battery, it would be by disconnecting this plug. And then the fuses also have the same layout basically as in the plus. The negative fuse is the closest to the inside, and the positive fuse is the closest to the outside. The light compact flash card is not accessible without completely disassembling the light processor layer. The light compact flash card is between the processor layer and the power layer. To fit the processor into the light form factor, the processor layer design used for the plus was split into 2 layers. The functionality is still the same. Our calling this the eDAQ processor is actually not accurate, as the processor layer also contains the power supply for the entire eDAQ stack. Internal components that may adversely affect our test would be the processor layer, signal conditioning layers, the battery as we've seen, and then memory or data storage. External components that may adversely affect our test would be power, okay, as the eDAQ must be powered by an external source, and inadequate power is a common problem. Environment, the negative environment would be predominantly extreme, heat or cold. Very rarely do we see problems caused by heat outside of the specification of the eDAQ. More commonly, we see startup problems caused by the eDAQ being below -20 C at startup. By system demands, we mean the test parameters and channel count that is solely up to the test engineer setting up the test. The eDAQ may or may not react well to being placed under these demands. Okay, we will discuss this later on. Chapter 2, Troubleshooting Aids. Front panel LEDs. Well documented in the manual and TC help. Oftentimes, the simplest indications can be effective at helping resolve the present problem. Become familiar with the LED sequence for boot up and power down reset. Almost all problems, including the loss of communications, are preceded by an eDAQ reset. It's important to note, whenever possible, what was occurring when this happened. A large share of loss of communications problems occur at the very beginning of the test. This is often an indication of a TCE setup problem, and the problem is normally noted in the log file. While it would be nice to use actual LED pictures or video, it is not possible in this format. We will use the simple color notation system shown here. The webinar format is not blinking light friendly. So in this example, we're showing the initial power state of all 3 LEDs on. Okay, our second troubleshooting aid could be the eDAQ log file. The log file, while somewhat cryptic in appearance, can be a very useful troubleshooting tool. It will list all the events that have occurred until it fills 4 pages. You will then lose the oldest log file data. Log files list the most current event at the bottom of the log file. Here we show an excerpt of an eDAQ log file. It's just a basic run start and run stop. Okay, also please note that the eDAQ log file uses connector designations from TCE. So here we show the F1 or the hardware setup page in TCE, just a cutout of it, and the connector designations are listed there, and that's how they normally appear in our log file. As an example, here are 2 excerpts of actual log files. We can tell from these that there is a problem with our DIO layer in the first one, and in our second one there's a problem with the VBM. Okay, sometimes this is all the information we need to isolate the problem. Another troubleshooting aid is your own expertise and skills of observation. Not to oversimplify this, but we sometimes overlook the obvious when we let a problem overwhelm us. This can easily happen as deadlines approach, and our frustration that the test won't run causes us to lose sight of what has happened. My most common initial question when confronted with an eDAQ that won't cooperate is, what has changed? Was there one channel change in the setup? Did you adjust just one more parameter in your vehicle bus database? Did the vehicle power system require some type of repair? These questions are just a representation of what might have happened to render your current test a no-go. Chapter 3, Most Common Problems. The most common reported fault is, my eDAQ has lost communication with my computer. This is normally reported as an intermittent problem or that it only occurs when the test is started. Possible causes are listed here, and we will look at these as we progress today. Shown here is the standard loss of communications window from TCE. Some of our normal causes would be cable connections or the power supply, faulty setups, reset caused by one of the conditioning layers, and then a faulty computer. On the previous slide, one of our causes is a faulty computer. This is a broad term used to describe computer setup problems, lack of knowledge of the eDAQ IP address, or external causes such as port blocking put into place by your IT department. Lost or forgotten IP address? Follow the eDAQ manual section shown here, 2.2.2, for using the serial connection. As a last resort, and only if you have access to another known working compact flash card, should you insert it into the eDAQ for your to get an IP address. The IP address is held on the compact flash. Another common problem is a death spiral lockout. It's caused when the eDAQ toggles between the main power supply and its internal backup battery 10 times over a period of 5 seconds or less. The eDAQ powers down the layer to prevent the internal backup battery from draining quickly. This situation occurs when the main power supply is a slowly discharging battery, such as a vehicle battery that is not actively recharging. It's indicated as shown here by alternating flashing red and green LEDs at 4 Hertz. To summarize this fault, if you receive it, there is something wrong with your power supply. This function was put into place to prevent a syndrome referred to as Monday morning eDAQ. We would often receive calls in regards to this. Normally they would occur after a weekend. An eDAQ would be left on, powered on by a vehicle battery. It would slowly drain the battery down until it started oscillating on and off. This would occur until the operator arrived to start the vehicle, or in the worst cases, the eDAQ eventually would lock up with all 3 LEDs lit. It would not reboot, would often have to be sent to the factory for work. This lockout has almost completely eliminated this type of problem. So here's just a look at our backup battery operating procedure, because it does affect the death spiral lockout, and then it's also just good general information. Okay, officially the good range for eDAQ power is 10 to 55 volts. But in reality, if you're down close to 10, you're flirting with possible problems. The approximate death spiral voltage level is 9.5 volts. The toggling that we talked about on the previous slide would be between 9.9 or 9.5 volts and 10. Okay, also we show here that between 6 and 9.5 volts, the battery will hold the eDAQ up for 10 to 30 seconds before shutdown. This is what we would call our cold cranking zone. And then if power dips below 6 volts, the eDAQ will shut down no matter what. Although if power rises back up above 10 volts, the eDAQ will power back up. Another most common problem is a device overflow or buffer overflow. Okay, the problem will first show up in TCE as this TCE error window. This fault is one of the eDAQ error flags. An error flag will reset the eDAQ. If it occurs during a test run, it will reset and start over. On the third failed attempt, it will stop. When queried in TCE, this error message will appear. When you select OK on this message, it will take you to the help page for eliminating overflow errors. Here's just a quick example of a log file that shows a buffer overflow error reset. Please that the line right above where I have the buffer overflow outlined, it calls out an HLSS layer at fault. But this error flag is caused by an overload of data. As an example, okay, here are 9 different test scenarios we use to test maximum channel count capabilities. For a quick example, please note the differences between test 1 and test 4 here. We use different data types, and in test 4 we used computed channels, whereas in test 1 we did not. Okay, so the results for each test setup are shown here, and this table would be a good table to use for estimation purposes. Please note that at 5,000 Hertz, for example, for test 1, we could get a maximum of 112 channels to run. And then channel 4, with its setup being the 32-bit by 16-bit we used in the first test, and the addition of some computed channels, we were only able to get 75 channels to run at 5,000 Hertz. Okay. If you would like to receive this complete document, please contact contact us at technical support. Here we show another error flag warning from TCE, the card exception error. Okay. These should not be confused with status flags. Status flags report an abnormal condition that does not reset the eDAQ. Therefore, they rarely cause problems in the field. Card exception errors are a result of an error flag. There are 14 error flags in the eDAQ. They're all listed in the eDAQ manual in section 10.3.2. Error flags, as I said, always cause a reset. And the most common error flag, as we show here, is a card exception error. We'll look at this closer in our review of eDAQ log files. Chapter 4, Troubleshooting with LEDs. LED status is well documented in TC help. Here we will concentrate on the most common field occurrences with suggestions for overcoming the issue. First, let's discuss the normal LED boot up sequence. Our first step, as seen here, is all 3 LEDs are on. During this time, the power controller chip in the eDAQ is really the only thing that's on, and it goes around and starts up everything else. Once the red LED extinguishes, the eDAQ has started the processor and attempted to acquire the boot information from the internal compact flash card. The eDAQ will continue until the yellow LED extinguishes, which signifies that a successful boot up has occurred. You should be able to now access your eDAQ through the web browser, or TECE. If the 3 LEDs stay on, then the power controller itself may not have started correctly. If you suffer this problem, the best thing to do is remove the external power plug and allow the eDAQ to shut down. Try to power it back up again. If it fails again, remove the bottom plate of your eDAQ and disconnect the NiCad battery for a few seconds. Reconnect it and see if the problem clears. What this does is reset the power controller. If that doesn't clear it, you will need to contact technical support. Green and yellow stuck on usually means that the eDAQ has not finished the boot up sequence. If you're unable to communicate via the web browser when the eDAQ displays this LED sequence, it is an indication that the boot up failed early in the process. Oftentimes it is an indication that the boot compact flash card is faulty or corrupt. However, like with any computer, we always want to try to power reset the unit a few times before troubleshooting further. If a reset doesn't change the symptoms, then replace the internal compact flash with a known good bootable compact flash card. You cannot just insert an off-the-shelf compact flash. It must be a bootable compact flash. Contact technical support if you need procedures to replace the internal compact flash. Okay. We also have the 2 LEDs stuck on when communications is working with a web browser. And at this point, communications with TCE will not work. The web browser will have a message that the eDAQ web server has not started. Please contact technical support. While we would like to talk to you about this issue, the action items listed here are what we would recommend if you call us. Attempt to reflash the processor firmware via the web browser. Check the power supply. The last event that occurs during the eDAQ boot up is that power is turned on to all the layers. An inadequate supply will cause it not to complete the boot sequence. And then as a last resort, as we talked about previously, would be to change out the bootable internal compact flash card. Okay, a blown fuse. Both LEDs blink simultaneously at the rate shown here. Okay, sometimes both blow and then no LEDs will light, but oftentimes it's just one. Okay, action here would be gain access to the fuses and check. We saw we had to take the bottom plate off of the eDAQ light to get at the fuses. However, you that own pluses know there is a fuse access door on the bottom that has 2 Phillips screws in it. You can easily gain access to your fuses that way. I know there's a number of people in the field that have eDAQs in enclosures or in situations where it's hard to get at, as you've expressed your discontentment with where we have the fuses on eDAQ before, but that is where they are located. Okay, our next was a power fault, so that would be both the red and the yellow LED stuck on. Okay, possible power supply problem. It could be possibly a wiring problem, and a faulty layer can also cause this problem. There are also many eDAQ lights in the field that have input power specs of 10 to 18 volts. If you're using an 18-volt supply or something close to 18 volts, sometimes that supply is just over the input spec and it will bring on the power fault indication here. Okay, other action would be check your power supply, remove connected transducers layer by layer, and then if there's no change, then you would end up having to remove the layers by one until the fault clears. And obviously, if the fault doesn't clear, you have an actual power supply problem in that eDAQ, and it will need to be sent in for repair. Okay, the red LED can be an indication of a fatal event or just a warning notice. As I said before, the test will stop after 3 attempts at running a test interrupted by a fatal error flag. Check the eDAQ manual section 10.3.2 error flags for all the conditions that would result in this. Then go to TCE for amplifying information as to the fault condition. The web browser can only display the fault condition via the log file. So if your test stops for some unexplained reason, this is probably what the LED state will be. The red LED set as a flag or a status flag warning, shown here on the bottom, will not stop a reboot during a test. As we can see, this could be an actual running eDAQ as your yellow light is blinking at 8 Hertz as your normal run would show on the front, with green on, and then the red on would signify that you have a status flag warning. Okay. The most common is PCM disk full and PCM access error. This LED state will indicate something needs to be checked, but it is not fatal. PCM disk full indicates there is no more storage space available on the compact flash memory. This error applies to both the external and internal cards on the plus, and obviously the internal card on the light. As we know, only one of these, either the internal or external, can be used at the same time. They do not work together. PCM access error is more common for the external slot. It would occur when someone removed the card before the test was ended, or usually it occurs when people are hot swapping cards and they don't follow the right procedure. Chapter 5, Troubleshooting using TCE or a log file. TCE, otherwise known as Test Control Environment, is a must for any detailed troubleshooting. Use features of TCE for fault isolation. You could reproduce the problem using the DVM function, which is probably the most widely used. Okay. We will often receive calls that the excitation voltage is too low. Sometimes the reason is that the channel is being checked without either the test being initialized or the DVM function is not active for that channel. This can also be valuable for troubleshooting wiring problems. The DVM can also help to isolate a known problem noted in the log file. Card exception errors can often be reproduced using the DVM function. So what you would do is highlight the channels that you want to check. Sometimes it will only allow you to DVM up to 16 channels at a time. Hit the DVM button, and it basically does all the same functions as TCE would do. It supplies power to the unit, and it actually starts polling those channels. I know that many of you receive files from the field and also reports of problems. And if you have a complete data file from a test, you can extract both the setup file and the log file from the data file. Okay, so you would go into TCE, and in the upper left-hand corner in your file selections, you would just select Open SIE or SIF file, browse to that file, and then you would select keyword extraction options as shown here, then TCE setup file to PC file, and then this will take you to the Windows file save function, and then you can name and save your TCE file. Then we would extract a log file from that same data file. And so from our same options, we would go back, we would select FCS log file to PC file, save the log file to known location. So now we would, from a data file, we would have extracted both the TCE setup for that test and also the log file. There are two other methods to access a log file. The first is through TCE. We would go to the L question mark icon on the top. Once you've clicked on this icon, you'll be able to save the text file. The advantage of collecting the log file through TCE is that your configuration will be shown. And that brings up something I would like to touch on. Sometimes layers, due to various internal problems, will not ID. When that happens, TCE will reorder your channels and create confusion. For example, when we only have one HLSS layer, as shown here, if it fails to ID, it will be very evident. But when you're running multiple layers of the same type, when they disappear, the connector IDs change to fill in the gap for the missing one. That can create confusion. For example, with 5 HLSS layers and the HLSS2 fails to ID, TCE will change the connector ID of HLSS3, 4, and 5 to fill in the gap. Most people will eventually catch this problem, but it has driven some of our customers crazy. The second way to collect a log file is through the web browser. Connect to your eDAQ via the web browser and select the Test tab. Then select View eDAQ Logbook. There is no configuration information in this logbook, but all of the other information will match the logbook you acquired via TCE. Now that we have a log file, what are we looking at? We need to concentrate on critical information. Can you find what you need here? Initially, looking at a complete log file can be intimidating, but once we realize that we only need to concentrate on the most recent entries, it becomes easier. Remember, the last thing that happened is on the bottom of the log file. Just a side note, if your vision is not that great, such as mine, do what I do. Copy and paste the log file into Word and change the larger font to allow you to see it better. Here's a different view with some key parameters highlighted. Okay. The event occurs before the time it occurred. So this is obviously a 24-hour clock. So the test started at 20:49 or 8:49 p.m. for you who are not 24-hour clock current. Our next test run started, or our test run stopped on an error at 20:49. The error was the TCE vehicle bus. So then we also have our power status as shown here, which we will talk about in just a few minutes. And then another important fact that is here is our TCE build version. Okay, here are two different sections of log files we have received. The second one shows a very common log file problem. This unit's battery needs to be charged, or it was low and the clock was reset. Take the time to reset the clock. It makes it easier to troubleshoot when you know the time the problem occurred. Especially critical when troubleshooting networked eDAQ problems. Once the clock has been reset, you have to set it via TCE. I know this sounds simple, but we always receive questions about how do I set the clock. To set the eDAQ clock, go to TCE and select Set FCS Clock. FCS stands for Field Computer System, which means the eDAQ. The only option you will have is to set the eDAQ to match the connected computer's clock. If for some reason that is not what you want, then change your computer clock to the time you want. Select Yes and your eDAQ clock will set. If the clock was set and does not match your local computer time, then you need to change your time zone. Time zone change is done via the web browser. Once you have set your time zone correctly, your internal eDAQ clock should be on local time. Now that our clock is set, let's take a look at a normal log file. Okay. So our first entry here, it means that on March 5th of 2013, our eDAQ finished booting up at 2207. It booted up running 318 firmware. At 2241, we finished initializing our test, which has a file name of test. At 2241, we prepped and started a test run. We stopped the test run at 2242, so the test has a total run time of 50 seconds. This is important to note for those times when you think your test should have run longer. The total test time is available in the log file. Okay, after 3 runs, we decide we've had enough and power down our unit at 2247. The power down event was done using the eDAQ front panel switch. Please note here that user switch can be the front panel switch or the remote power leads on the eDAQ power cable. Unexplained user switch power down sequences can either be the remote power leads or a faulty switch. The next few entries in this section deserve their own page. Here I disconnected the power source to turn off the eDAQ. Please note the power loss entry by the user switch entry that we had on the previous log file. If you end up with many more runs of data than you thought you had collected, take a look at the log file for multiple power loss entries. You may have an intermittent power connection. The next line I have broken down into the 5 significant parts. The first bat charge is a measure of how far through the charge cycle this battery has been. This doesn't indicate that the charge cycle has been successful, just that it has been charging a certain amount of time and should have 92% of the current available that the battery is rated for. The second entry, bat volt, is the voltage of your battery. The battery shown is a good battery. If you were to look at a log file and the bat charge is in the 90% range and the battery voltage is 10.5 or below, it's time to start buying a new battery. The third entry is bat sense. This is only an indication of current direction and is not normally that great of a troubleshooting aid. The fourth entry is very important, as this is what the eDAQ sees as the power supply voltage. This eDAQ is being run off of a 24-volt supply. Please note that this is the voltage the eDAQ sees, and this is obviously a pretty good troubleshooting tool. The fifth entry, DC to DC volt, shows the voltage level being supplied by the processor layer to the other layers. The other layers in the eDAQ all have their own power regulators that they use to regulate the DC power they're receiving from the processor. Okay. This parameter will follow your input power from 10 to 18 volts. So for example, if our supply voltage was 11 volts, our DC to DC voltage would be very close to 11. Okay, but once it hits the 18 volt level, an internal regulator will kick in the processor layer, and it will keep our DC to DC voltage at 15 volts, as our signal processing layers don't really want to see anything above basically 20 volts. And for you guys out there that use 48 volt supplies, obviously we don't want to be supplying our layers with 48 volts. Okay, the last entry is bat temp. This is an RTD that is placed in the battery. If you have an eDAQ that shows a temp of minus 19.9 C and won't start up, then the eDAQ needs to be heated up before it will start. So the keys here really are battery voltage and supply voltage, and then I would say maybe possibly battery temp after that. Sorry, I forgot to run through these real quick as I did this, but hopefully you saw them. Okay, here's a common example of a problem battery. While it appears that the battery has almost completed its charge, the battery voltage is a problem. Note here that our last entry after power up shows that our clock rolled back to 1999. The internal battery is made up of 9 cells. When they start going bad, your voltage will go below the desired minimum 10.5 range. Notice I said desired. Most people will say a battery is okay at 10 volts, but if you see a voltage level below 10.5 after the eDAQ has been charging for 4 hours, go ahead and start ordering a new battery. Okay, here's an abnormal log file. Actually, we saw this log file earlier. Now let's move in and see if we can figure out what the problem is. Our first indication shows that there is a discrepancy between the mask and value parameters of the vehicle bus database we're using. Okay. Now, that may not be real clear to a lot of people, but the big indicator here is the second indicator, and it's our TCE vehicle bus. So we know we've got a problem from what we can tell with our database and our TCE vehicle bus. So how do we isolate that? Well, you can recreate the problem by using the DVM function. Okay, vehicle bus database errors will show up and reset the eDAQ exactly the same way using the DVM function. There's no reason to run a sample test to check them. So I would just use the standard half split method. If you have 20 channels, split them into 2 groups of 10 and see which group of 10 resets the eDAQ, and then narrow it down from there. Now, some of you may be savvy enough with your database to realize what's close to line 14 in your database, or can pull that up, and that's fine also if you want to zero in quickly that way. But a lot of people out in the field are just basically, hey, what's going on, and gee, how can I figure out how to get there quickly? So to me, this is kind of just a quick way if you're out there to figure out what channel might be causing my problems. Okay, here's another log file representation, or another log file with a common problem showing our infamous death spiral lockout. Okay, please note that this was done, there wasn't a test running when this happened. I mean, this death spiral lockout is going to occur whenever that power scenario that we talked about previously occurs. Okay, here's a common DIO problem. We know that DIO 1 has a problem. The exception message here points to bank B. Can you see that here? Okay, if you drop out the percentages, the percentage signs, and the 20 in the exception message, then you'll get bank B output drive fault. Okay, this percentage and the 20 are space holders that are used by the programmers, and they'll cloud our view, but if you take them out of there, normally you'll get some type of message that makes a little bit more sense to you. And the output driver fault error itself is somewhat misleading. It's caused by negative going below 0 volt pulses on a digital input on DIO channels 1 through 8 on any bank. Okay, you can either correct it by eliminating the negative going pulse or move the input to channels 9 through 12. They can tolerate negative going pulses. So here's another example, troubleshooting with a log file, and we just need to focus on where the fault is. There's a lot of information here, but we just want to know where the fault is. So our first indication would be we do see a line here that says HLSS channel 3, excitation voltage, but then our question would be, well, what HLSS? As we all know, there's a lot of systems out there with 4, 5, and 6 HLS boards. Well, we have to go down a ways to find, but we find slot HLSS_2, which is how it is noted in TCE underneath in the connector field, as we noted earlier. So we now know that it's HLSS2, and it's also channel 3. So now that we know that, we can zero in on the problem and correct it. Okay, so this is really a good example of how knowing what area to focus on can help us narrow down the problem. This actual problem was caused by a failed SMART module, but if you would have noted in the log file, if you wanted to go through all those lines, there was really no mention of a SMART module failure in our log file. This problem could be easily taken care of by moving the cable to another channel and see if the problem follows the cable. Chapter 6. Okay, special cases, networking, and vehicle bus. Okay, look upon networking as nothing more than synchronizing multiple eDAQs off of one master sync reference timing pulse. Okay, you can use quite honestly, any infinite number of eDAQ classics, pluses, or lights can all be networked to each other. So if you have a classic, a plus, and a light, and networking cables, you can get all three of them to work together. The only caveat there would be is that they all need to be running the same version of TCE. So if you throw a classic in there, you're going to have to dumb everybody else down to 3.9. Okay, I mean, we're only sharing a common timing pulse, and all the eDAQs have the same capability. So this is easy to troubleshoot using log files and substitution. Verify setup using the eDAQ manual section 4.8. It is a very good guide if you've never done networking before. If you follow that guide step by step, you should not have any problem to network your eDAQs. And the hardware needed is listed in the manual section 2.5.1. And the hardware section also lists the cable part numbers that are needed, and it also will break out, how many of each of these cables will you need, for example, to network 3 eDAQs. So the most common problem in networking is the slaves do not start. This is easy to see using the front panel indications. When initialized, both the master and the slaves will be waiting to start. So we show here the green light will be on, and you have the 1 hertz yellow, or the yellow LED will be blinking at 1 hertz. Okay. So then we start the master, and it will go to on with our 8 hertz blinking yellow LED, and then the slaves will follow very shortly after with the exact same front panel indications. If the slave does not start, there are 2 possible problems. The timing signal circuitry is faulty, or the sync cable between the 2 is faulty. You can isolate this by swapping the master and slave in TCE. Okay, this will change the circuitry being used. And rather than having the output driver from that master and the input receiver on the slave, you swapped them, and then you can tell if one of those is at fault. But if that doesn't change any symptoms, then I would just swap out the sync cable that is carrying the master timing pulse. Okay, here we show normal master-slave log files. I know that the slave internal clock is 1 second ahead of the master here, but that's really kind of a moot point. This is not important, as the internal clock is being used to timestamp events here. The important thing is that the slave started in sequence. The slave starts after it receives the MSR clock signal and stops when the MSR clock stops, as noted in the slave log file below. When you see just before test run start, you see no MSR clock. It senses the MSR clock is stopped, so it stops. Just as a quick note, for a set of hardwired networked eDAQ systems, the data acquired on all the slave nodes lead the data acquired on the master node by approximately 1 to 2 microseconds. The reason for this is that there is a 1 to 2 microsecond delay in the propagation of the sample clock signal from the master to the slaves. Okay, so there's a problem that occurred in this example. Okay, please note here that the master ran for 3 more minutes than the slave. The master, as we said before, only sends out a master sync reference pulse and doesn't receive any feedback at all from the slaves. So the slave had lost power 3 minutes before we ended the test and stopped, as shown down in below when it says power down event. Any reset or power loss reset to a networked eDAQ will result in that eDAQ going to the initialized state and waiting for the master to start again. If the master loses power or resets, it will also return to the initialized state and wait to be started. So our next thing we're going to talk about is vehicle bus. This is basically just to discuss hardware setup. We will not discuss database generation. This webinar is, quite honestly, it's a subject all on its own. Okay, vehicle bus problems are divided between basic connectivity and database problems. Both problems can look identical. Always verify hardware operation first. There's 3 hardware operations for vehicle bus. ECOM layer, as shown here, embedded in, or this is just a single ECOM layer, not embedded in the processor. The vehicle bus module connected to the DIO layer, and our legacy layer, the high-level board vehicle bus layer, HLB-VB, which there aren't that many left out in the field anymore. Okay, so here's a screenshot in our web browser of a system that has all 3 vehicle bus hardware options. Please note under card type the vehicle bus hyperlinks. Clicking on any of these links will take us to the vehicle bus page. So here we show the vehicle bus page for our eDAQ shown in the previous slide. Note that all the vehicle bus options are available here. For our purposes, we only need to concern ourselves with one drop-down, and that is the baud rate, obviously after selecting whichever CAN network that we want to use. And for this example, we would want to use CAN 1 because that's where we have our wiring. So after verifying your wiring, including the vehicle bus termination, select the baud rate that your CAN source is running at. And once we have selected the correct baud rate and verified our hardware connection, we should be able to stream raw vehicle bus data. You do not need to make any other selections. Just select the Log CAN 1 Messages button. If your hardware is connected correctly, the web page should fill up with raw CAN data. If you do not get this data stream, check your wiring, bus termination, and baud rate. Once you have verified your CAN hardware connection, you can proceed with your setup in TCE. You can then verify your database by using the DVM function of TCE and start testing. Simple, right? Our vehicle bus problems, especially hardware related, this occurs quite often, and normally we do solve it over the phone or via email using the exact same process that I just showed here. And it is much more simple than people think. Most of those parameters that we've shown on our web browser page, you don't even need to set. You don't have to have a database selection. All we want to make sure is that we're connected correctly to the network, terminated correctly, and can stream raw hex data. Okay, just a quick summary today of some important points. Keep your internal backup battery healthy. Pay attention to your front panel LEDs if possible. Double check your power supply when things happen that can't be quickly explained. And then try and quickly identify the faulty layer using a log file. If assistance is needed, contact support@usa.hbm.com and attach your TCE setup file and log file, and we will sure try and help you as best we can. Questions?
All right, John, thank you. Everyone, you'll find the Q&A button up at the top of your screen, and you're welcome to type questions in there, and we'll get John to respond to them. I will send the presentation out to everyone who attended, so if you want it for reference, you will have it. We also record these sessions, and so I'll also notify you when the recording's available online for on-demand viewing. John, reading one question, is there a way to clear out the log file?
Yeah, there's a couple ways you can clear it out. You can go into TCE, and in the top toolbar, I believe it's the same one we pulled down for set FCS clock. It's format RAM disk. If you hit format RAM disk, it'll clear out the log file completely. If you're running CIF, it'll also clear out your CIF data, but that shouldn't be a real concern to most people. And then also, if you went into the web browser and reflash the firmware on the processor, it would also clear out the log file.
All right. If I'm currently running TCE version 3.14, should I upgrade?
That's a fairly common question, not just in pertaining to that version, but specifically talking about that version. Yeah, I would upgrade. There was a bug in 3.14 that it was not that frequent, but it would corrupt the internal compact flash card. And as you remember our slide with the yellow and green LED on without any communications, it would corrupt the card bad enough to where you would need to replace the card. And then also, we've made some changes in our streaming video capabilities in our later versions. So I would suggest in your case, yes, it would not be a bad idea to upgrade. 3.18 is currently available on our webpage.
New question, how likely is there to be a problem with the compact flash card that requires replacing it with another bootable card? They're wondering if they should make sure to have a spare bootable card handy.
If I was a guy running tests in the field and I was going to take anything with me, I'd take a spare internal compact flash card, bootable compact flash card with me. Okay, it just with power dropouts and the card itself going bad, because it's really hard to tell when these compact flashes go bad. They get a bad spot on them, but sometimes it can be intermittent, and you know, it doesn't take much to have an extra 4 GB internal compact flash card tucked in your pocket, quite honestly. So I would make it a point to have one in my desk drawer also, as I do.
Different question. Should the internal battery protect against eDAQ restart during tractor startup? They're having issues with their eDAQ restarting and wondering if that indicates a battery issue.
You know, it very well could be. And take a look at the parameters that I showed you today, but also check and see is it being pulled down below the 6-volt level? It normally shouldn't be. Okay, but that could also create the same problem. It's either the battery or your cold cranking operation is going down below 6 volts.
All right. Well, everyone, if you come up with any other questions in the next few days, you're welcome to email support@usa.hbm.com, and John or somebody else will get back to you. Thank you very much for joining us today, and we hope to talk to you soon. Have a good afternoon.
Thanks.